it happens that I write too small font, please feel free to stop me and let me know. It's just, as I said, after a few lectures I stop. I start to forget about it, so please remind me. Okay, so I guess first let me briefly review the last lecture, just very quick. So last lecture we talked about these two important concepts, underfitting and overfitting. So I guess so here our goal is to make the generalization work, right? So we want to generalize to unseen examples. So and last time we talked about two possible reasons for why your test error is not good enough, right? So one possible reason is overfitting. So overfitting means that your training error is actually pretty good. Your training loss is pretty small, but your test loss is pretty high. So, and we have discussed the possible reasons for why you can have overfitting. And two possible reasons are if maybe you have too complex of model. For example, last time we discussed that if you use a 50-degree polynomial for this very, very small data set where you only have like 4 examples, then you may overfit. Or maybe you don't have enough data, right? If you have more and more data, if you have like a million data, then a 50-degree polynomial wouldn't be a problem. And also we discussed that and another reason, underfitting. So underfitting is much easier. Underfitting in some sense basically just means that you don't have small enough training loss or training error, right? So your model is just not powerful enough so that you cannot even fit to the training data you have. So and in some sense these are kind of like two complementary situations, right? So in this case you probably want to make your model more expressive, and in this case you maybe want to make your model less expressive or less complex. So we use this word complex expressive a lot without a formal definition, right? So we say some models are more complex, some models are less complex. Typically you can somehow feel it, right? So a 50-degree polynomial probably is more complex than a linear model. But actually, if you really want to have a concrete definition, it becomes a little bit tricky, right? So what is the right complexity measure of the model? Someone asked about that as well in the last lecture. And the answer is that there's no universal measure for what's the right complexity measure. And there are a few, kind of like complex measures people often use. They all have their kind of like particular strengths, and they have like and also like there's no real kind of like a formal theory to say which one is better. So these are kind of complex measures that can be theoretically kind of justified in certain cases, but they are not kind of like universal. So what are the complex measures? So I'm just listing a few just for kind of like for your knowledge in some sense. So I guess the most obvious one is how many parameters there are, right? So if you have more parameters, then your model might be more complex. And this is very intuitive. However, the limitation here is that maybe you have a lot of parameters, but you actually the effective complexity of the model is very, very low. Maybe all the parameters are very, very small. Then maybe you can say, in this case, maybe the complexity is actually not as big as you thought. So to kind of like deal with this kind of like scaling thing, right? So what if all your parameters are kind of basically 0, even though you have a million parameters? Then people consider kind of like norms of the parameters, right? But this may not be. This is actually typically the norms of parameters. It's actually very good. They are very good complex measures for linear models. And this basically before deep learning kind of like arised, before I think we were using norms as complex measures a lot, and still we use them in some cases. But this also has limitations. For example, sometimes you may, for example, one adversarial case it would be that you have a very low norm solution, and you add some random kind of like a noise to the model. And when you add the noise, you make the norm bigger. But actually, the noise doesn't really change the complexity, right? Because you add some noise, and when you take the matrix multiplication, you average out the noise to some extent. So these are, there are also these kind of like issues. So some of the other kind of more modern complex measures people have considered are, for example, something like Lipschitzness, right? Whether your model is Lipschitzness is Lipschitz, or maybe your model is smooth enough. And here I'm using the word smooth in a relatively kind of like informal way. This could mean the bound on the second order derivative. It could mean the bound on the third order derivative, something like that. If your model is kind of like not kind of like oscillating or kind of fluctuating a lot, maybe that means it's not very complex. And there are other kind of like complex measures, for example, how invariant your model is with respect to, for example, certain translations, certain invariances that you should have in a data set. For example, whether your model is invariant to data augmentation. But in general, there's no kind of like a very kind of established theory on what is exactly the right complex measure. And sometimes it also depends on the data, as we will see today. So if your data, sometimes for example, suppose your data, for example, let's talk about norms, right? So different norms, what are the norms? Are you talking about L1 norm, L2 norm? Sometimes L2 norm is the right complex measure for a certain type of data, and sometimes L1 norm is the right complex measure for a certain type of data. So basically, I don't think this is kind of like there's anything super concrete we can, it's not like I have a kind of like just a fixed like a suggestion for you to consider. So in some sense, you should just keep this in mind and kind of consider them, when you do your own data set. So this is the okay. So now we have discussed the complexity measures, and now in the rest of the lecture, I think I'm going to cover two things. So one thing is that once you have some kind of like guess on what's the right complex measure you are looking for, how do you make the complex measure small, right? So how do you encourage the model to have small complexity, right? So it's easier to do this because you just change how many kind of neurons or how many kind of like hidden variables in your deep networks, right? You can change the number of parameters. But if you want to change the norm, what do you do? So that's called regularization. I'm going to discuss that, in the first half of the lecture, and then in the second half of the lecture, I'm going to talk about, how do you, I'm going to talk about, some kind of more general ML advice. For example, how do you tune your hyperparameters? When you do regularization or when you kind of like choose your model complexity, right? You're going to use a lot of hyperparameters, meaning you're going to choose how many parameters you have. You're going to choose, how strong your regularization is. So how do you tune your hyperparameters? And on what data set you should tune your hyperparameters. And at the end, I'm going to probably spend 30 minutes on even more applied angle about some ML advice, right? So for example, how do you design the ML system, from scratch? There are a lot more things in reality, more than what you do in research. So that part I'll use some slides to talk about some general ideas on how do you design ML system in reality. So that's the general kind of introduction of this course, of this lecture. I'm going to start with regularization. Any questions so far? So regularization. I think we have probably mentioned this thing sometimes like in the previous kind of lectures, just because just because we have mentioned this informally. So by regularization, mostly we just mean that you add some additional term in your training loss to encourage low complexity models. So for example, we use J of theta as our training loss, and then you consider this so-called regularized loss, where you add a term lambda times r theta. So here, this r theta is often called regularizer. And lambda is, I think there are different names for this, but you could call it regularization strength. Or regularization coefficient, regularization parameter, regularization strength, whatever you call it. Maybe let's call it regularization strength. So this lambda is a scalar, and r of theta is a function of theta, which will change as theta changes. So, and the goal of this r of theta is to add additional kind of like encouragement to find model theta such that r of theta is small. So for example, typical r of theta could be something like L2 regularization. So you say r of theta, one possible choice is that you take This is probably the most common choice. You take the L2 norm square, and you multiply by half. The half doesn't really matter. This is just some kind of convention. Because anyway you're going to multiply a lambda in front of it. So whether you have half or not here, we just change your choice of lambda. But just this is just a convention. And so this is called L2 regularization. Also in deep learning, people call it weight decay. There's a reason why people call it weight decay, I guess. Probably I wouldn't have time to discuss it today. So in the lecture notes, there's a very short paragraph. You can see actually if you use this regularization, then the update rule will look like a weight decay. So there's one step in the update rule where you decay your parameter, you shrink your parameter by scalar. So, but anyway, so it's just the name. Like either you call it weight decay, you call it L2 regularization. So that's one of the pretty common one. So and you can see that if you add this thing to your loss function and you're minimizing your loss function, so then you are trying to make both the loss small and also make the L2 norm of your parameter small. And the lambda in some sense is kind of like controlling the trade-off between these two terms, right? If you take lambda too big, then you only focus on the regularization. You just only focus on a low norm solution, but maybe you don't fit your data very well. If you take lambda to be for example, 0, literally 0, then you are not using your regularization. You are just only fitting your data. And actually, when you make the lambda very, very small, this can still do something. Right? So even say, let's say lambda is 0.00001, right? Very small. Still, this might do something because maybe there are multiple theta such that j of theta is really, really close to 0, or maybe even literally close to 0. So if you don't have this, then you are not doing any tie breaking, right? If you literally make lambda 0, then you are just picking one of the solutions where j theta is 0, but you don't know which one you pick. But even as long as you add a little bit of regularization, then you are using this as a tiebreaker in some sense. So you are finding some solutions such that j theta is very, very small, but you use the norm as a tiebreaker among all of these solutions that have very small training loss. So this is probably the most typical regularization people use. And another one is the following. So you can take r theta to be the so-called zero norm of the parameter. But actually, this is not really a norm. This is just a notation. So this is really just defined to be the number of non-zeros in the model, in theta. So you count how many non-zero entries in theta, and that's what this notation is for. Sometimes people call it zero norm, but it's actually not a norm, literally. It's just the number of non-zeros in the parameter. And sometimes people call this sparsity, because if you have very few non-zero entries, then it's sparse. Otherwise, it's dense. So if you add this to the thing, then you're going to have a different effect. You are trying to say that I'm going to find a model such that the number of non-zeros in it is small. And this is particularly meaningful for linear models in the following sense, because if you think of this theta as a linear model, then say you have theta transpose x, right? Suppose you have a linear model. And then what is this? This is really just sum of theta I xi, I from 1 to d. And then you can see that the number of non-zeros is really how many, if suppose you have like s non-zero entries in theta, that means that you are using only s of the coordinates of x size. So basically, the number of non-zeros is in theta is the number of coordinates or number of features you are using from xi. Right? So you can imagine that maybe, for example, for some applications, you have a lot of coordinates in your features, in your input features. Right? So you have so many different kind of informations, but you don't know which one you should use to predict. Right? So for example, suppose you want to predict the price of a house, then you have so many different features, but some features may not be that useful. So then you can imagine that that could be a situation where you should use this as a regularizer, because you want to say, I want to use as few features as possible, but also I want to make sure my training loss is good. Right? So I want to find the simplest explanations of the existing data, or simplest meaning that you want to use as few features as possible. So, and once you find this theta such that theta is sparse, right? So suppose you have a theta such that you only have a few non-zeros, in theta, then you are selecting the right feature. So in some sense, you have a sparse model. Means you are selecting the features, right? Because those non-zeros correspond to those features that are selected by the model. So people often call this kind of like a feature selections in certain kind of contexts. So, however, you may have realized that this regularizer as a function of theta, this sparsity one, is not differentiable, right? So you're just counting how many non-zeros they are, right? So suppose you have one. Suppose you have one entry that is maybe say theta is just 0, 0, 0, right? You do an infinitesimal change in this in any of the coordinates. You are going to change this function, the value of this function by a lot. So that's why it's not differentiable, right? A differentiable function should satisfy that if you change theta infinitesimally small, then you should change the function output by a small amount. But actually here, if you currently the sparsity is 0, but if you change theta a little bit, your sparsity becomes 1. So you can have infinitesimal small changes to make the regularizer value change by a large amount. So that's why it's not differentiable. So it's not because it's not differentiable, then you don't have gradients, you don't have like derivatives. So that causes a problem in using this. So basically, even though I told you this is a regularizer, but literally in reality nobody uses this exactly in their algorithm, because if you use it, you get this, you put it here, but this term has no gradient. How do you optimize it? So because it's non-differentiable, so then what people do is that you have a surrogate. So this is a typical surrogate. The reason why this is surrogate is a little bit kind of tricky, but this is has been a surrogate for the sparsity. So this is a differentiable surrogate for the sparsity of the model. So you use the one norm. So here one norm just means the sum of the F's value. Is the sum of the F's value of each coordinate. So, and you can see, I wouldn't attempt to give you a very formal justification for why this is a good surrogate for the 0. One reason could be that you can see at least one norm is closer than 2 norm to 0 norm, right? One is closer to 0 than 2, and another reason probably this is not really very solid mathematical reason, but it's just to give you some intuition. So suppose you think of theta as a vector in 0, 1. Suppose you really just have a binary vector, then indeed this is equals to this, right? So that's probably another kind of intuitive reason why they are somewhat kind of like related. But you can see a lot of problems with this argument, right? So why I'm assuming theta is only taking value from 0 and 1, right? So if they are from 0 and 2, then these two are no longer that related anymore. So I'm not saying that this is really a good argument for why they are related. So if you really want to say they are related, or this is a good surrogate, I think you have to go through much more math. Any questions so far?
First norm regularizer with the second norm regularizer.
You mean the one norm and two norm?
Yes.
Okay, yes, that's what I'm going to do next. So, all right. So that's a great question. So why you want to encourage sparsity sometimes, and sometimes you want to encourage the two norm to be small. Right, so let's answer that question. Let's think of this as a surrogate for the sparsity. So the question I'm trying to answer is why sometimes this is better, sometimes this is better. So in some sense, the fundamental reason is just that in some sense the regularization. Another way to think about regularization, instead of just encouraging low complexity, is that regularization can also impose structures, kind of like prior beliefs about the theta. So this is probably another, at least one of the other ways to think of regularization. This also imposes structures this, what are the structures? The structures, probably sometimes means you have a prior belief. So for example, suppose you believe, you have a prior belief because of domain knowledge, right? So such that you somehow believe that theta is sparse. Right, so in sparse theta. Then in this case, you probably should just use R theta is the 1 norm or the 0 norm. Just because you believe that your model is sparse, why not just encourage that, right? So this, when you have this belief, then you should say, okay, so if you encourage the 1 norm, then you're in some sense you limit your search space, right? So you limit your search space. Before you are searching over all possible parameters, and now you're only searching over low 1 norm parameters. And because you believe that your true model is having low norm, then even narrowing your search space is always, narrowing your search space is always helping you, because you didn't lose anything, right? Because you know that every model that you excluded are not going to be the right solution. So you narrow your search space. The new search space still has the right model, then why not do it? So that's another interpretation of the regularizer. So it's trying to it can impose additional prior belief in the structure of the model, right? So if you believe in L1 norm, then you should encourage L1 norm. If you believe that your true model has a small L2 norm, then you should encourage small L2 norm. And if you get into more mathematical theory, I think L2 norm typically corresponds to situations where you believe that all the features are useful, but you have to use them in a combination, right? So you have to use each of the features a little bit. And L1 norm or L0 norm typically corresponds to situations where you believe only a subset of the features are meaningful, and you should discard other ones because other ones are just kind of like are there to confuse you in some sense. So if you believe your model is sparse, then you should use L1 norm. And if you believe your model shouldn't be sparse, then typically people use L2 norm. So, and if you have a linear model, so suppose you have a linear model, and then this loss, if you use this L1 norm regularizer, this is called lasso. I guess I'm just defining the name because I think it's probably useful for you to at least heard of this name, this acronym once. Actually, I don't know what it originally stands for, but this is this has been there for 20 or 30 years, which is a very, very important algorithm. For linear model, you apply L1 norm regularization, and it's called lasso. Everyone in machine learning should know the acronym. So, right. And taking a little bit more broader perspective, so if you think about a nonlinear models, like deep learning models, so what are the most popular regularizers these days? I think L1 norm is not used very often, and actually pretty much it's never used. I don't know exactly how frequent it is, but I think probably less than 10% of the model use L1 regularizer. Maybe even less than that. 10% probably is much overestimate. Maybe 1%. So but the L2 regularization is almost always used. Even though sometimes you only use a very weak L2 regularization. I'm talking about deep learning model. So sorry, maybe let me just clarify. For linear models, people tried. You can try almost anything. Anything would be reasonable, and you probably should try all of them. You could try 1 norm, 2 norm, and sometimes you can try different norms, which I didn't write down. But you can try 1.5 norm, something like that. So for nonlinear model, for deep learning models, I think basically L2 norm is something that you almost always use, but you only use it with relatively small lambda. People generally don't use very large lambda. I don't know exactly what's the reason. Researchers don't really know that much either, but a small L2 regularization is typically useful for deep learning. And in deep learning, I think some of the other regularizations could be useful. For example, you can try to regularize the Lipschitzness of the model. And you can try to use data augmentation, which we haven't discussed. I'm going to discuss that in a later lecture, but you can use data augmentation, which tries to encourage your model to be invariant with respect to kind of translation, cropping, these kind of things for images. I think those are pretty much the only regularization techniques in deep learning. Yeah. Any question?
So would you suggest, like, and this kind of a selfish question, this kind of pertains to math earlier. Yeah. Would you suggest initially using the L1 norm to kind of eliminate the features and then going on to use the L2 norm?
That's a very good question. So I think this kind of algorithm was pretty popular in for before deep learning era. So when you use linear models, I think using L1 to do a selection and then you use L2, I think, I don't know exactly how popular they are, but this is definitely one algorithm people you could try to use. In deep learning, I think is probably a bit less likely to be useful, but also depends on the situation. For example, if you don't have enough data, maybe you are more or less in a linear model case, right? You just need the nonlinearity to help you a little bit. Maybe then in that case, you should still mostly use some kind of more like linear model type of approach. If you are in the typical deep learning setting, for example, you do for a vision project, right? You have images, right, as your inputs. I think in those cases, you probably don't want to select your features first. I think all the inputs are useful, and you want to use them as much as possible, and you just want to let the neural networks to figure out what's the best way to use those inputs. Any other questions? By the way, this lecture will be pretty we don't have a lot of math, right? Most of the things are about I don't think there's even theory here. Sometimes they are just experiences, because especially if you talk about the modern machine learning in the last 5 years, right? So everything seems to change a little bit, right? So I cannot say anything with 100% guarantee. I can only say, okay, it sounds like people are doing this a lot. And that's the bad thing I can tell you in some sense. So feel free to ask any questions. Any other questions? Right. So, and the next thing I'm going to discuss is the so-called implicit regularization effect. And this relates more to the deep learning. And so one reason that people started to think about this is that, I haven't told you what exactly it means. So one motivation that people started this line of research is that people realize that in deep learning, you don't use a lot of regularization technique, right? So you use L2, as I said, you only use a weak L2 regularization. And often some of these ellipticness ones, right, they only help a little bit, right? They can be useful, but people don't necessarily use them very often. So why in deep learning, you don't have to use strong regularization? At least you can feel that the regularization stop mattering that much. It still matters when you really care about the final performance. You care about 95 versus 97%, but you don't have to, even you don't use regularization, sometimes you get reasonably good performance. So that's why people, especially theoretical researchers, people are wondering why you don't need to use strong regularizations in deep learning. And this is particularly mysterious because in deep learning, people are using over-parameterization. Like we are in this regime where you have more parameters than the number of samples. Recall that in the last lecture, we have drawn this double descent thing, right, where you have this kind of things. Right? Here is the number of parameters. And this is the test error. And we have kind of discussed that this peak might be just something about the suboptimality of the algorithm, which let's say you don't care for the moment. But at least you have to care about why here, why is going down still here, right? So why when you have so many parameters, a lot more parameters, you can still make your model generalize. And it seems that more and more parameters makes it looks better. So the over-parameterized regime is kind of mysterious because you don't use strong regularization, but you can still generalize. So that was the kind of the motivation for people to study this. And people realized that there's, even though in this regime, suppose you don't use any explicit regularizer, you make that lambda 0, literally 0, right, in this regime. Still, it can generalize. And the reason it can generalize in many cases is because you can still have some implicit regularization effect even without explicit regularizer. And where that effect comes from, what kind of make that happen? The reason is that the optimization process, the optimization algorithm, the optimizers can implicitly regularize you. So why this can happen? I think the reason is that, let me draw a kind of like illustrative kind of figure, which I kind of like use pretty often. So suppose this is the, let's say this is the parameter. Like suppose you have this is the loss landscape, the loss surface. So meaning that here is theta, let's say theta is one-dimensional. And because we are in this deep learning setting where we have like a nonlinear models and non-convex loss function, so maybe a loss function, it looks like this, maybe. So this is the loss function. And you have maybe you have multiple global minima of your loss function, right? So this is a global minimum, this is a global minimum. But you have multiple global minima in your loss function. However, I'm talking about training loss, right? If you really look at the test loss, they will look a little bit different. The test loss would be different from the training loss. So test loss maybe look like something like this. Maybe, okay, let me draw something according to my figure so that. So this is the training loss. Test loss probably look like this. So that means that even though both of these two global minima are good solutions from the training loss perspective, one of them is better from the test performance perspective, right? This global minimum is better than this global minimum because the test performance is better. So, and in some sense, like the regularization effect is trying to choose the right global minimum, right? You want the regularization effect to choose the right global minimum. So that you can do some tie breaking or you can encourage certain kind of models. Maybe this model is more kind of like Lipschitz or this model has smaller norm than this model. So that's why you prefer this one. So if you use explicit regularization, what you do is that you're going to say, I'm going to change the training loss. I'm going to add something to prefer this one than this one. I'm going to reshape the training loss. Right? That's what the explicit regularization would do. But the implicit regularization would do is the following. So if you consider an algorithm that optimizes this. For example, suppose you run an algorithm. This algorithm just always initialize. This is initialization. And you do gradient descent. So you're going to do something like this. And you converge to this one. So this algorithm will only converge to this one, but not this one. Just because you initialize at this far right. Right? So that is kind of, in some sense, a preference to converge to this global minimum over this global minimum. Because your algorithm somehow prefer one global minimum than the other, just because your algorithm has some certain specifics, right? So the initialization make it to prefer to converge to this one. And there could be other kind of effects. For example, if you use bigger step size, maybe you are more likely to converge to this one, maybe, or maybe vice versa, depending on kind of like the situations, right? So this is a very illustrative thing with one dimension, then you don't really have a lot of like flexibility here. But if you have a very, very complex thing, then if you run different algorithm will converge to different global minimum. And that preference to certain type of global minimum is in some sense is a regularization effect, so that you don't converge to an arbitrary global minimum. Does it make some sense?
Can you just repeat what you said? So how does like having a large number of parameters ensure that it initializes at that point?
Yeah, I was silent on that in some sense. Like I didn't really say why the initialization has to be here. Like this is an active area of research. So what we are sure about is that the algorithm could have this effect. The algorithm could possibly prefer certain kind of global minimum than the others. But why it would prefer which kind of global minimum, we don't exactly know. For certain kind of like toy cases, we know, but for the general cases, we don't. I'm going to show you one cases where we actually can say what does the algorithm prefer to do. But that's very, very simple case. For general case, I think the research, this is still a very open research question. I saw two other questions here.
This seems like the optimizer is choosing a number of parameters. It doesn't quite make sense to me.
Here what do you mean by the non-optimizers?
What is on the axis?
The axis is the value of the parameter. It's just they only have one parameter. I'm drawing the landscape of the parameter, and I can only draw something in one dimension. So this is the value of the parameter. You are just tuning this parameter. You are doing good instant, and this is the loss surface. So it does depend on where you initialize, right? So if you initialize at different places, you're going to converge to different global minimum, and they may have different generalization effect.
So in practice, would you use multiple different algorithms and then just choose the one that has the best performance?
That's pretty much the right thing to do. Of course, there are some. I'm going to discuss this in a bit more detail later. But basically, like you can have some intuition. We have the theoreticians have tried to understand what kind of like algorithms can help generalization. But I think the conclusion, at least so far, is not. Is very far from conclusive. They can give you some intuition, but they are not going to be like predictive. They are not going to just tell you like what to do. So you still have to try a lot. Yeah. So yeah, going back to this, this is just one dimension. Another way to think about it is that if you can think of like a two-dimensional question. For example, you are skiing in the ski resort, right? So your objective is basically minimizing your you're trying to go downhill, right? That's your objective. So and the ski resort probably have a lot of villages, right? Like that you can eventually go home. There are multiple parking lots, right? So you like in some sense you are saying that one of these parking lots is great, right? So one of these parking lot is really where you are. So you want to go to that one. But different algorithm would lead you to converge to different parking lots, right? So for example, someone is doing very fast skiing, then when you do it, then you cannot go to those kind of small trails, so then you go to one of the parking lot, and some other one prefers like wider kind of like trails, and then you go to the other parking lot. So different algorithm will lead you to different parking lot, and different parking lots have different generalization performance eventually. Yeah. So this is the high level intuition. So I'm going to let's see. I'm going to discuss a concrete case, which will also be part of a homework question. So this concrete case, just to give you a concrete sense on how this could even be possible. So I'm going to show you the high-level thing, and there is some mathematical part which will be in the homework. So this is the linear. This is in a linear model. So interestingly, even though this implicit regularization effect was mostly discovered after deep learning started to be kind of like powerful, but actually you can still see it in linear models, and that's how researchers start to do research. So let's say suppose we are just in the most vanilla linear model setting where you have some n data points. This is just the trivial linear regression. And your loss function is something like just the L2 loss, the mean squared error. Something like this. You have a linear model. But let's make the one different thing is that we assume n is much smaller than d. So you have very few examples and very high dimension. So what is d? D is the dimension of the data. And n is the number of examples. I'm going to assume n is much smaller than d. So this is over-parameterized. You have multiple global minimum. Why you have so first of all, you have multiple global minimum. Why? Because I'm claiming that there are minus theta such that minus theta satisfies yi is equals to theta transpose xi for all I. Why? Because how many equations here you have, right? So if you want to, so this is the equation to make training loss 0, right? Which means global minimum, right? So if you have all of this equality, then it means you are at a global minimum of this training loss. And why there are multiple theta such that you can satisfy this? That's because you can count how many equations there are, right? So there are n equations, right? And d variables. And these are linear equations, right? So I guess the linear algebra tells us that if you have n equations, d variables, and if n is less than I think if n is less than d, or d minus 1, I think n is less than d, then you're going to have at least one solution. And if n is much, much smaller than d, then you're going to have a subspace of solutions. And that's called what's the kernels of the, anyway, you have a subspace of solutions for this kind of linear system equations. Right, so, and that's why you're going to have multiple global minimum of the tuning loss, because the entire subspace of solutions are global minimum of the tuning loss. So the question is, which one you're going to converge to, right? So which one your optimizer will choose. So it turns out that if you use gradient descent with zero initialization, then you're going to choose the one with the minimum L2 norm. So here is the claim. So the claim is that if you do gradient descent with initialization, theta is 0, this will converge to the minimum norm solution. So what does the minimum norm solution mean? Formula, it means that you converge to the solution with the smallest L2 norm among those solutions such that those global minimum of the loss function. So when you use gradient descent, you are not only just finding a theta such that the loss function is 0, right? So typically, when you think about optimization, the optimization is trying to find a solution such that the loss function is minimized, right? That's true. You definitely find a solution such that the loss function is minimized, but you actually have a tie-breaking effect among those solutions such that the loss function is minimized. You actually choose the one with the smallest L2 norm. So I guess, in some sense, the kind of intuition is the following. So I'm going to try to draw this. It's a little bit, I need to try to draw this well. So suppose you have, let's say the intuition is that let's say you have n is 1. And say d is 3. So you just have one equation, one linear equation, and and you have like 3 variables. So that means that the family of solutions is a 2-dimensional subspace. So let me try to draw this. Okay, so here the subspace I'm drawing here is, this is the family of theta such that you satisfy that the loss is 0. Right, this is the subspace. Right, so you have a subspace of solutions, but which solution you converge to? That's the question. It turns out that if you start with, let me see, maybe I will write here. It turns out that you're going to find a solution such that this is the solution you're going to find. This is the solution. How do I draw this? Drawing this is a little bit challenging, I guess. How did I do this? I think I did this. So you consider that you projected 0 to this subspace, right? So that you find this point. This point is the solution with the minimum norm that is closest to 0 on the subspace. And this is the solution that you will find. You're not going to find other solutions with gradient descent with initialization 0. So basically that's the claim. The claim is that you're going to find this particular solution but not the other solutions. And the reason is actually, fundamentally the reason is pretty simple, like especially if I draw it in this way. Of course, if you want to prove it, it's a little bit more complicated. So the reason is really just that you start with 0. This is where you start with, right, within this set. And you have a property such that when you, how do I, maybe let's erase this. So you have a property such that if you start with, if initial is 0, right, and then at any time, so your theta is always in the span of all the data points. Here I only have actually one data point, so I'm only so basically your theta cannot move arbitrarily in any places. So you only have a restriction on where the theta can go. So actually for this particular case, what happens is really just that you are just moving it along this direction until you find this point that hits the subspace. And that's what the gradient descent is doing. So gradient descent will not do something like this. We will not converge to here. It will not converge to here. It will just go to this this closest point, right? The point that is closest to 0 on the subspace. So this is clearly a property of the optimizers, right? You can imagine you may have other optimizers. Suppose you design some crazy optimizer which does this or does this. Then you will converge to a different point. But if you use gradient descent, you're going to do this. And the main property you show that the gradient descent is doing this is by saying that the gradient descent is always in the span of the data. I think this is actually something we have proved in the kernel lecture. I'm not sure for a different purpose, not for this purpose. Remember that in the kernel lecture we try to show that your parameter is always in a linear combination of the data, and then there the purpose was that you want to represent it by the betas in that lecture. So it's a different reason, but it's different goal, but it's the same fact, right? Your theta is always in the span of the data.
So are you saying that the optimal theta is in the span? It's always in the span of the data.
The optimal, no. This span is defined to be all the solutions that have 0 loss. So these are all the span is. That's my definition of the subspace. This is the family of solutions that have 0 training loss. So, and the question is which one I'm going to converge to. I mean, kind of like I was arguing that, there are multiple global minima, right? So this whole span are global minima. All of them are global minima. And which one you want to converge to? So different algorithm probably would converge to different points. So if you run gradient descent, you're going to converge to one particular one in this span. Right, but this phenomenon also shows up in other cases, but they're going to be much more kind of complicated. Like I think there are only a very limited number of situations where we can theoretically prove where you converge to. But it's almost always the case that the optimizer has some preferences. The optimizer will not converge to an arbitrary 0 training loss solution. It will converge to one particular 0 training loss solution, and sometimes that solution just generalizes much better than the other ones.
So for the parameter is the span of data. So is that only one for linear models or?
Right. So only for linear models, the family of zero loss solution is a span, right? So if you have nonlinear models, then the family of solutions satisfying this wouldn't be a span. Maybe it's a manifold, some other weird structure, right? So in that sense, this is very special.
Okay, I understand that it's like this, we're going to converge to a solution that's going to be in that span. How are we sure it's going to be that it's going to be that constrained optimization problem that we just saw, that like it's going to constrain itself to this like minimizing the second norm, right?
Right. So I didn't show you the full proof. So this point turns out to be the point that you converge to turns out to be the minimum norm solution. And it turns out that you're just going straight in, at least for this n is 1 case. So it's not even always true that you are going in a straight line, but you always go in this subspace. So am I answering the question? Maybe I didn't.
I'm just asking, can you prove that?
You can prove it. I think the homework question actually asks you to prove that you're going to converge. This point is exactly the minimum norm solution, and also you're going to converge to that. So
okay.
actually, you can have a pretty concrete representation of this point, right? It's really just some inverse sum of the matrix times something. You can compute what exactly it is, and you can show you converge to the point. I'm not sure whether the homework asks you to show. I think the homework asks you to show both. But we will have a lot of hints, along the way. It's not going to be just show this. That's it. And maybe, for example, just to give you a sense on what these kind of things can change, right? Suppose you initialize here, then you wouldn't converge to here, so you probably would converge to somewhere here. And if you use stochastic linear descent, you probably wouldn't converge to exactly here either. You'll probably converge to somewhere differently. So where do you exactly converge to? It's a very hard question. We don't really know. We only know that the only thing we know right now, I think, firmly is that this matters. If you use different algorithms, you converge to different solutions, and different solutions generalize differently. So you have to consider the effect of the optimizers. And going back to this, the reason here is really, so I guess, this in some sense, this kind of is trying to explain why you can generalize here. That's because of this implicit regularization effect, even though you don't have regularizers, you still implicitly regularize the L2 norm. So, and that's why in this regime, even though you have a lot of parameters, but actually you are still implicitly regularizing the L2 norm. And if you look at the norm would look like this. So this is the norm as you change the parameter. So basically this is saying that when you have a lot of parameters, actually your real norm is actually relatively small. And that's why you can generalize. So the reason why you don't generalize in the middle is because this minimum norm solution is not actually doing well in the middle for some other reason. So the norm actually turns out to be big, but actually the norm is very small in the over parameters regime, even though you use a lot of parameters. Okay, so now let's talk about how do you really do how do you really find out what's the I've told you that we don't know too much about how does the optimizer change things, right? So we also don't know exactly how does the model complexity change things, right? So you only know some intuitions, right? So you know that if you have more complexity, it turns out to be more likely to overfit, but you don't know exactly what is the right complexity, right? So how do you find out the right model, the right optimization algorithm, the right regularizer, all of this, right? You have so many decisions, right? You probably have like 10 decisions you have to make in this machine learning algorithm. So how do you find out what's the best thing? So I think the typical way is just that you use a validation set to figure out what's the best decision. So maybe just to motivate that, just briefly, so the easiest way to do it is that you just use a test set, right? So you have some test set, and you try all kind of algorithms, all kind of models, all kind of regularization strength, and you see which one has the best performance on a tested set. So that's okay as long as you only use the test set at the end, right? So you try all of these algorithms in advance, and then you collect some test set, or maybe you collect the test set before, but you never touch it, right? So that's okay. So if you only use the test set once, then you can use the test set to evaluate the performance of all possible algorithms, or all possible kind of models you want to use. So that's a good thing. So however, the problem is that sometimes you want to do this iteratively. You want to look at a test set and see what the performance is, and then you go back to say, okay, maybe I'll change my model size, right? Or maybe I'll change my my optimizer, right? So maybe I'll change from gradient descent to stochastic gradient descent, maybe I want to add some regularization effect, add some regularization like a function. So so if you don't do it iteratively, then what I said before was not going to work. That's because, you know, so typically if you have a test set, you can only use it once. So because if you use it multiple times, what happens is that you could kind of like overfit to the test set. So basically your later decision becomes kind of like a overfit. Our decisions overfitting to the test set you have seen before. So the validity of the test set is only ensured when you only see the test set after you do the training. So, and if you see the test set and then you do the training and then you test it again, then the second time you test on the test set, it will be not guaranteed to be valid. So you may overfit to the test set. So does it make sense? I'm trying to be not over complicate this, right? So that's why I'm trying to use informal words for it. But if there's any questions, right? So how do we deal with this, right? So the test set we can only use it once, or at least we can only use it. We cannot use it interactively. You cannot see the test set, train, and then see the test set again. So one way to deal with this is that you have a holdout, you have a validation set. So basically you split the data into 3 parts. So one part is called training set, and one part is called validation set, and also test set. And for test set, this is your kind of like this is very, you have to be like very careful about it. You shouldn't touch it. This test set is only at the very, very end you are using the test set to evaluate your performance. So, but the validation set, you use this to tune hyperparameters. And by hyperparameters here, I mean all the kind of like the type of parameters that you are choosing. For example, the batch size, you know, the lambda in the regularization. Maybe the choice of the optimizer, the number of neurons you're going to use in deep learning in your deep learning model, how long you're going to train, you know, all of these, you know, decisions that you are going to decide in this process, they are called hyperparameters. And so you are using the validation set to tune the hyperparameters, and you are using the training set to tune the real parameters, right? To optimize the parameters, right? So I guess typically we don't know, so to tune the parameters. Right, these parameters are just the numerical numbers, right, in the model, which anyway you don't know where the meanings are. But the hyperparameters are those kind of things that you know their meanings, right? Batch size, learning rate, step size, right? So they all have some meanings, and you want to use this validation set to tune the hyperparameters. So basically the kind of process is that you start with the training, and then you start with training with some hyperparameters, and then you validate your performance. And then you go back to tune again, maybe using some other hyperparameters, and then you do this iteration for many times. So, and after you are done with everything, and you found out a model that you are happy with, which, you know, by you are happy with, I mean that you found out a model that is very good on a validation set, then you finally test your model on a test set, and that can be only done once. So in some sense, I'm not sure how many of you have seen this Kaggle computation, right? It's kind of structured exactly like this. So there's this online platform where people release their data set and set up some kind of like challenge, right, for people to submit their machine learning model to solve their tasks. So basically, in the Kaggle computation, so they have the organizer have a test set which nobody can touch at all. Like this test set is only used once at the very end when you decide who is the winner. So, but and then the organizer released this too. Actually, I'm not sure. Sometimes they give you a division, right? So they say this is the validation set, this is the training set. Sometimes they just release the total, all of them to you, and then you can divide yourself. You know, even they release in this format, you can redivide them. You know, whatever you want to do. So let's say suppose you have divided your, you know, all the training example into these two sets. You can do whatever kind of like optimization you want. So, and I think typically they do have like a designated validation set which is used for computing the scores on the leaderboard. Right? There's a leaderboard which kind of like tells you how well you are doing against others, at least temporarily. Right? So that's the validation set. That's evaluated on the validation set. But this leaderboard may not be exactly the same as the final rank. It's possible that finally you found out that somebody is succeeding in the leaderboard, but eventually in the very final test, the performance is not as good as the validation set suggests. But this is the general setup that people are doing. Does it make sense? So one common question, that people kind of like generally ask, which I ask myself as well, is that how reliable this validation set is, right? So like if you have very high performance on the validation set, should you trust yourself? So on one side, you shouldn't trust yourself, 100%, because if you can trust your validation set performance, why you need a test set? But a test set is supposed to give you the final verdict in some sense, right? It's a very it's something that guarantees to give you the right answer. So the validation set is never 100%. You probably shouldn't 100% trust it. So on the other hand, empirically, so people realized in the last 5 years that I think there is a sequence of paper on this. People realized that actually the validation set performance, is actually well correlated with the test set. So this is a reasonable indicator about how good your performance is on test set. It's just there's no theoretical guarantee that these two are exactly the same. So, but in most of the cases, if you don't do anything crazy, you don't kind of like somehow just memorize the entire validation set by creating some kind of lookup table kind of things, then typically your validation set performance, the performance on the validation set is kind of very close to test set. And this has, there's a very important paper in probably 3 or 4 years ago by Berkeley people. So they actually look at maybe 300 Kaggle computations, and they are they look at the best performance, the rank of the performance on the validation set on the leaderboard, and they look at how they correlated with the final winner, the final performance, and they found that they are very correlated. So which suggests that the validation set is actually a pretty good indicator for the test set, even though it's not guaranteed. And in these days, the typical machine learning the typical machine learning kind of practice is that if you look at when people publish papers, right? So in some sense, people publish results based on the validation set. So for example, if you look at ImageNet performance, right? In some sense, people are the so-called test performance that people report is actually a performance on the validation set, because that so-called test set has been seen so many times. I think actually it's I don't know exactly whether there's a label, name for it, like in the ImageNet, the official data set, but at least that set, that you report your performance with, that set shouldn't be considered as a test set, because test set you should only use it once. But actually people have used it so many times, maybe 1 million times. So basically, abstractly speaking, I think these days when you publish a paper, you use the validation set. Only when you have the Kaggle computation, you use the test set to really decide the winner. But empirically, it sounds like they are very close. So actually, that's why we're not worried too much about it. Any questions?
What's the name of the competition?
I think it's called Kaggle or Kaggle. I don't know how to pronounce it. Right. This is a platform. So the platform hosts a lot of competitions, maybe 100 every year or something like that. You can submit your model, and sometimes there is a there is a prize for winning the competition. Yeah. So right. And by the way, I think this validation set, sometimes now people call it development set as well. I don't know how popular this name is, but at least if you say validation set, I think everyone would know what you're talking about. Development set, I think most people would know as well, but it's a relatively new term in the last 5 years.
Question on using randomized training sets and validation sets as part of a bigger. So once essentially you've decided on what hyperparameters you want to use, you kind of have that aggregate training and validation set and just choose those randomly.
Right. Right. So how do you do the split, right? So here, so the most typical way is that you just split randomly. You reserve probably a tenth of the data set as validation set, maybe 20%, depending on how many data you have. So and I think what you are probably thinking is this so-called cross-validation, which does something much more complicated. You can kind of split your data set into you can do multiple splits and try multiple experiments on different splits. So I think I think I'm not going to cover it for this lecture, mostly because I think these days, if you have a large enough data set, typically you just do this static split. Just because it's much easier, you don't have to run the algorithm multiple times, and this is just almost like like in most of the larger scale machine learning situations, you just use this. So, but if you just have like 100 examples, then indeed, as you said, if you fix like 20 examples as validation set, it's a little kind of like wasteful. So then you have to do some cross-validation. So we have a kind of like a section in the lecture notes about cross-validation. There's a description of the practical. I think if you're interested, you can read it. It's nothing very complicated either. Okay, so I guess yeah. So I'm going to use the last 20 minutes to talk about some more applied perspective. I'm going to use the slides. So I guess I will. Can work. Okay, great. So it's not centered, is it? Wait. Okay, sounds good. Okay, good. So so I think this lecture. So we are talking about some ML device. So I think so here these slides are made by our other instructor Chris Ray. With the help of Alex Radner. I'm pretty much just repeating whatever he's saying in the slides. So I think the slides used to be a little bit longer than this. I'm going to release the longer version as well. So I shortened it to only 20 minutes or 30 minutes. And part of the reason is that I think the slides also contain something that has been covered on the blackboard, on the whiteboard. And also part of the reason is that there are some applied part which I think we don't have a lot of time to discuss in this quarter. So, but I'm going to release the longer slides as well for your reference. So this set of slides are mostly for kind of like a little bit more applied kind of like situations. For example, you are thinking that you are, for example, you're a startup and you are doing machine learning to solve some concrete problems, right? So so it's a bit less like a research because you're going to see that you're going to have much more issues than a concrete research setting, right? So in research, actually, you sometimes also have this, right? In research, the most typical setting is that you probably have a very concrete data set, right? You know the input, output, you know everything. There's no any room in flexibility. You cannot redefine the problem, and you just want to get the best number. That's one type of research. I don't think this is the most typical one either, right? But this is one type of research. And then from there, you can have more and more flexibility. You can change your data. You can rephrase your problem. You can find out what's the right problem. And once you really do it in industry, then it's going to be much more complicated. So and some disclaimers to start with. I think this is Chris' disclaimer, which is also mine. So these are like there's no universal kind of like what is ground truth here, right? So there's no ground truth. It's really just some experiences and some experiences from people doing it in real life. So and things change over time. Sometimes people thought that was the right thing to do 5 years ago, and now things changed. So I'm going to go through this a little bit quickly. So but I'm going to omit some of details as well. But feel free to stop me. Right. So there are many. So in some sense, there are many phases of ML project if you really do it in industry, right? So for example, one thing you want to discuss is that you really need an ML system even to start with, right? Some of the questions are not really necessarily suitable for ML. I think at least I don't do as much industry work, as Chris is also an entrepreneur. Besides, a professor, so he knows a lot about this. But even I know that sometimes, people actually, when they really sell their product as an ML system, but actually the underlying system is not really using much ML. So sometimes you don't really need ML. And when you use the ML, if it doesn't work, what do you do? So and also how do you deal with all the kind of ecosystem? So, and when I use the random example, we're going to have a spam detector, and the question is how do you detect spams? We use this example a lot in this course. So this is the 7 steps for ML system. So here again, it's a little broader than just the ML research, right? So you're thinking about designing a system that can actually work in practice. So acquire data, and you want to look at the data. And maybe you want to create some kind of twin development test set, as we discussed. You want to define or refine specification, which I'm going to discuss. In some sense, this is saying that you have to have an evaluation metric for your model. In what sense you want your model to succeed? And then you want to build your model and try a bunch of models. Maybe you're going to spend a lot of time in step 5, and then you're eventually going to measure model's performance, not necessarily only according to the specification you have defined in step 4, but maybe you're going to have other measurements, for example, speed, training time, so on and so forth. And then eventually you have to repeat, and maybe you have to repeat a lot of times. So I'm going to go through these steps, relatively quickly. I only have 15 minutes. So, but you can kind of if you're interested, you can look at the longer slides as well. So suppose let's say you want to decide what is spam or not. So ideally, you want a data sample from the data that your stamp product will be run on, right? So you want to have your data to be somewhat kind of closer to the final test data, right? So you don't want to just collect some spam data from 30 years ago and use this data to train something that can work not these days. But sometimes this is not always available because you never know what the spam emails will be 10 years after, so you have to make some sacrifice. Sometimes you don't even have the features. Maybe your existing record didn't save everything. Maybe you just saved the title of the email, didn't save the entire content. Then that would limit your capability of detecting spam. And there are many legal issues to look at the data. And this is according to Chris. I think this is true as well. So you get it wrong on the first try, right? So sometimes you'll find out that the data you collect are not the right one. You have to repeat. And then, after you collect some data, you have to look at them, right? So, and this is something that we actually don't really teach a lot, in this machine learning course, looking at your data, right? Because, we are mostly assuming that you already have your data, you make the right assumption already. You already know your data is Gaussian, and then you are in Gaussian discriminative analysis, right? But we never say how do you decide whether you really make the assumption about the Gaussian assumption. So, but in practice, you have to do that because you have to see whether your data makes sense. And there are many nuances there. For example, sometimes your data are not as good as you think. Maybe there are some kind of maybe the format is not right. Maybe there are some kind of outliers, so on and so forth. And only if you look at the data, you kind of see what's going on there. So actually, even in research, sometimes I experience this, right? So I think in one of my projects, I think we just used the wrong data from day one in some sense. I think the data, some of the data were just corrupted, just by accident, and we are training on them. And until 1 month, I think we realized that. So of course, in research, it's probably easier to detect that. 1 month is a long time for us to detect it, I think. But actually, you can easily detect them. But for real life cases, sometimes it's even harder. For example, you don't even necessarily have the tools to look at your data. You maybe have to build some tools to look at your data. and you need to kind of like think about different subpopulations, maybe spams from edu emails or spams from .com emails, and see what are the differences. So this will give you a lot of intuitions on what data you should use and what kind of models you should use, and do this at every stage because like for example, when you really do the and this is also the reason why you want to build some tools to look at your data conveniently, right? So sometimes, like if you just look at it once, then sure, then you can just maybe print out something, right? So, but if you want to look at many times, then you should have some convenient tools, which actually eventually will reinforce and let you to more likely to look at data, right? So I think at least in research, I also realized this. So if the data is very hard to visualize, then people are less likely to visualize the data. So sometimes it requires an investment so that you can have this tool so that in the future you have less of kind of like cost to look at your data. And you should do this at every stage in many cases. So and this is I guess this is about domain knowledge, where you sometimes some of the data requires expertise, right? Like to know. So some I think there are some examples in the slides which I removed just to save some time. But like, in short, sometimes for example, if your data is corrupted, like only experts can know. Like for example, you have medical data, only experts can know that your data are corrupted. But like from a machine learner perspective, the data looks fine. So we talk about true and depth test split. So this of course is something important for you to do. And in practice, it's a bit less clear than in research, right? Because in research, sometimes you already got a split, even at the first place, right? So before, like you got the data already has a split. But in real life, sometimes you have to avoid certain kind of like a leakage. So for example, maybe sometimes, let me take an extreme case, right? So suppose your data has repetitions. So you have like 1 million data, but actually it's just like every data point is repeated twice. So essentially you just have 500K, but repeated twice. If that's the case, then you split the data, then you're going to see some repetitions between, like some examples in the test will also show up in the training exactly the same. So that would be a disaster. So you have to kind of avoid these kind of situations. And this actually happens in the Kaggle contest. So actually in many I try to do some of this Kaggle contests at some point. At least at that time, like that's probably 3 or 4 years ago, maybe more than 4 years ago, maybe 6 years ago. At that time, many of the contests. So if you look at there's always some kind of like forum for discussing like. Okay.
It's the one.
Okay.
Sorry.
No, yeah. So right. So like in this Kaggle, like I'm sure this happens more in the industry, which I'm not less familiar with. But even the Kaggle contest, so in many of the Kaggle contests, if you look at the forum, always after like a half a month, after a few weeks, someone will figure out some leakage, just because some examples are very, very close to test example, so that they just use this leakage to hack the number. So it's kind of like some kind of like weird rule so that you can make the validation performance much better than you thought. And everyone has to use that. And it's kind of interesting. I don't know why. Like everyone who found this kind of leakage, they always post it in the forum somehow. And then I don't know whether this is always true, but like for the few cases I've seen, they do this. And then everyone else will have to use this small gadget to improve their model performance. Because if you don't use it, your model performance is just not as good as others. So yeah, I don't know whether maybe they have some better ways to detect this leakage to design the computation much better. I don't know. So, but this is something you have to pay attention, in practice. And also another kind of tricky thing is that what is a good split? So we have discussed whether you should do random split, right? So in research, as I said, random split is pretty much the best way you can do because you really literally care about the validation performance. But the problem is that sometimes, in the real world, like your test, like the test data set is actually not really what you care about. So that's why when you split it, you also want to split the true and validation set in a way such that the validation set is somewhat closer to the real test set. So I guess this is the situation. So suppose you say you are thinking about stock price prediction, right? So your final goal is to predict the price in the future, right? So that's something that you just don't have at all, right? So so now suppose you have data between 2000 and 2020, right? So you have these 20 years of data. So how do you do the true validation split? Should you just do a random split, or you should do some other things? So one possible option is that you should probably split into, for example, 2000 to 2015. That's the true. And 2015 to 2020, that's the validation. Why you argue that? Why that's a possible option? Possibly just because the last 5 years is more predictive of the future than the early years. So I'm not necessarily saying that this is the only option or the best option, but this is at least something to consider, right? So this would this is not what we do in research. And the reason is just because like you care about the performance in the future, which is something you don't have access to, right? So I guess this is. Right, so the better split is to use the first 50 days to predict the last 50 days. So, okay, and create a specification, right? So I think this is mostly related to like how do you kind of like define what you want to predict, and what's the kind of the goal, right? So in many cases you can use machine learning model in many different ways, from what you wanted to use it, right? So and also you care about kind of different perspectives. For example, what is a spam, right? So like the definition of spam sometimes, are different between different people, right? So like maybe do you think like an ad, right, from say Google, do you think that as a spam? Maybe I would think of like that, but somebody else probably prefer to receive some ad emails with very low rate. Right, so you have to specify exactly what you want to predict, right? So what is really the definition of spam? And you don't want to have ambiguities, at least, right? From these days perspective, right? So like machine learning models don't like ambiguities. You really want to have a clear cut. What is the spam? What is not? And also like what level of expertise is required to understand it, because if you specify the spam, you can have a definition, but if your labeler are not able to label the spam according to your definition, it's not going to be useful, right? Suppose you have a very, very complex definition of spam, and then you say, I have this data, and I ask the labelers to label them, but the labelers cannot execute my definition of spam easily. That's going to be another issue. And also the specifications, like so you use this specification because you want to kind of like you use this specification to define a set of examples, right? So because eventually if you just have some kind of description, text description about what is a spam, that's probably not useful. You have to really have a set of test examples, and the test examples have labels, and that is really your definition of spam. So, and for example, one of the quick and dirty tests here is that whether your definition of the spam can pass this so-called inner annotator agreement. So basically what you say is that you write down some definition, and then you select some randomly selected, you get some examples of emails, and then you ask 3 annotators to see whether they can agree on which email is a spam or not, according to the definition you give them. And often you don't really get that high of agreement. You don't get 100% agreement. In many cases, people's interpretation of the same definition would be different. And let's say you have 95% agreement. I think that's already considered to be great. And then you have 95% agreement. Then the question becomes, whether it's meaningful to shoot for some accuracy more than 95%. Right? If the annotators don't agree with each other, only agree with each other on 95% of time, should your machine learning model do better than that? Actually, sometimes you can do better than that. just because humans are sometimes less have less accurate like interpretation. Sometimes machine model can do better, but typically you probably shouldn't shoot for much higher than 95% in many cases. So and then you are gonna do this iteratively. For example, you have to kind of examine the specifications. You're gonna look at what's the disagreement, why you have disagreement. Maybe that means you have changed your specification, and the last question is kind of interesting, right? Do you tune the people or the machine? Eventually, at some time, if you kind of have a lot of like a different, sometimes you have to tune the people to label them correctly, right? So, for example, even like the image classification problem, we have this clearly defined labels, right? So dog, cat, but once you go to the more the breeds of dogs, right? So some of the labelers don't really recognize different breeds of dogs. So you have to tune the labelers in some way. So I have a friend who did this like in PhD, and basically he has a lot of kind of tuning documents for the labelers, the Amazon macaque turkers, and they have to actually ask the turkers to pass some exams to be able to be a labeler for them. So it's actually kind of complicated. Okay, so I guess I'll be quick given that we are almost running out of time. So, and then when you do the model, this is the more machine learning part. So you want to implement the simplest possible model. So, and you keep it simple, and then, and sometimes I think this is this thing. So don't get bogged down in new models. Use them to understand data, right? So sometimes like the problem is that the models are not only the end goal. Sometimes you want to use the model to understand what are the problems with the data, right? So and sometimes you can fix the data, and then the performance becomes much better. So so this is a whole loop, right? Like your bottleneck may not just be only about the model. Sometimes it could come from some other places. Maybe the data, maybe the specification, maybe the train test split, so on and so forth. And you have some baselines so that you know what you are doing, and you need to do some ablation studies, so on and so forth. And then step 6, you need to measure the output. So you have to measure the output so that you don't make mistakes twice, and you want to catch new mistakes as soon as possible. And you want to measure kind of different things and simple things. For example, there are a bunch of kind of like quantities you care about here, and so on and so forth. And this is probably one thing that is one challenge that we are really facing these days about machine learning model. Maybe I would say probably one of the most important challenges. So the reason is that you have a distribution shift, right? So your training and validation distribution are very different from a distribution that you will test eventually. Or maybe they are similar, but there is some kind of like special subpopulations that make them different, right? So for example, you train on San Francisco street views, and then you test on Arizona street views. For example, when you build an autonomous driving car, then you train on some street views, and you have to test on some other places, and that creates a distribution shift, and then you can have surprises. There are not so many kind of like good ways to do this, except that you have to kind of be careful about it and design new algorithms. And this is incredibly hard, right? There's no real solutions in industry. I don't think there's real solutions in research either. So I think we're going to have one guest lecture by James Zhou about the robustness of machine learning models. There are a lot of recent work on it, but so far we don't have. I think we have definitely better algorithms to be more robust, but I think the performance is the robustness is still not ideal enough. Okay, so I think I will just jump to step 7. So yeah, you have to repeat and look at data. I will release the longer version of the slides, if you are interested in some of the details. Thanks.